Hi, everybody. Welcome to week 4 of the economics of cryptocurrency. To start out this week's video, I want to do a quick reminder, and this will be available to you in the, sorry, I forgot to share my screen and I just looked at it. So I wanted to show you this overview. You'll have access to this, of course. And what we're doing this week is cryptography. And so I just, as a quick reminder, our first week we did supply and demand, a general review of that from economics, and then briefly how it might apply to cryptocurrencies. And then we did money, prices, and volatility. We talked about the functions of money, because cryptocurrencies maybe can function as a money. That's a claim that's out there. We have assessed that a little bit already. You guys did a great job assessing that in your last assignment. And then volatility, of course, is something that came up. So some basic finance and the functions of money. And then last week we talked about balance sheets and digital money and those concepts. Today, or in this video, we're going to be talking about cryptography, which I'm thinking of kind of as the last building block we need before we really jump hardcore into cryptocurrencies. And that's the way the book is structured as well. As you can see, the next section of the book is called cryptocurrencies. So a lot of this so far has been building blocks. This may be the most complicated building block, especially given some of your backgrounds more in economics than things like math and computer science necessarily. But we're going to focus on the economic implications of cryptography in this lecture and this week, and really for the remainder of the semester, because those are really what are important to us as economists. I'm going to give you a little extra credit opportunity here. I will go ahead and give you a point on your midterm exam if you are the first to send me the answer to this little ciphertext that I made. One clue is that I have not encrypted the spaces or the question mark. So the question mark is valid. And then the length of the first word is 6 letters, for example. So the spaces and the words are the right length. And so this isn't necessarily related to the more complicated, like don't try to use our Python code to solve this. I tested on AI. AI could not solve this, at least in, well, I was using it. Maybe if you spent enough time with it, it could solve it. But you probably can solve it. Reading the book, how much time you should spend trying to solve it is a different question because trade-offs, of course, don't go over your opportunity cost on trying to solve it. But I thought that would just be like a fun little exercise that you could try out if you're looking for a riddle in your life. So let's go ahead. I'm going to basically walk through the collab for this entire lecture because it is a little bit computer sciencey. But again, we're going to be focusing on the economic implications of that computer science. So let's just jump right into it. At the top of our collab for this lecture, of course, we always put libraries on the top. We have some libraries that are going to help us with something called hashing and some other core cryptography functionality. And then we're also going to just import this because we'd like to print binary cryptographic objects in readable form. So we're just going to, the book goes over these as well. You're going to get different perspectives from the book. It's going to touch on different things. So it's important that you read the book and look at the lecture. Both of those will appear on things like quizzes, collab assignments, and exams. So it is important that you do each thing. And because these are probably new and complicated for a lot of you, I think that's another good reason to go ahead and use all of the resources that are available to you. And of course, I always recommend that you go seek other resources if we're not quite getting it, which could include meeting with me, reaching out to me with questions, or just looking for other resources online, brainstorming with AI. I think it's something I do to learn about new things and to come up with new ideas all the time. Don't have it come up with new ideas necessarily for you. Use it as a tool. You know, complements and substitutes. So I'll just say that quickly about AI. We want to be complementary to AI, right? Because that when AI becomes more productive, we become more productive too. We do not want to be substitutes for AI. And I think you can figure out why that is. So anytime you're interacting with AI, I think that's important. And it is important not to just let the AI do the work for you. That can lead to trouble, as maybe some of the comments on the most recent homework will point out for you. But I think this is a good class where you can sort of play around and see the power of AI while still reflecting on what is your power? What are you bringing to your relationship with AI? Anyway, moving on, hash functions. So a hash function is a function. So go back if you don't remember the definition of a function. That's hopefully something you've covered in math before you got to this course. But it takes an input, as all functions do, of any size, and it maps it to a fixed length output, that already is going to be an important characteristic for us. And that output is called a hash or a digest, I believe, or I think there are some other names for it as well. Hash functions serve several important roles in computing and economic systems. So some core properties of these functions that we call hash functions. One is that they are deterministic, they're not random. The same input always produces the same hash. And that's going to be a characteristic of a hash function that has economic meaning, which we'll see later in this lesson. They are one way. So given a hash, it is computationally infeasible to recover the original input. So we can do things like we can apply a hash function to a message, and then that will produce an output. We'll look at what that output looks like soon. What is very difficult, if we put that message in the hash function again, we'll get the same hash again or digest or output from the function. What's extremely difficult is going from that output back to the input. And that is another important characteristic that's going to have major implications for us of hash functions. They are very sensitive to changes. This is one of the reasons. These are related. One of the reasons it's really difficult to go from the output back to the input is that they're sensitive to changes. If I change the input just a little bit and the output changes just a little bit, that might make it easier for somebody to use an algorithm to back out what the original messages are. And we'll see that that's something that we don't want to be a characteristic of hash functions, being able to figure out the input based on the output. They are also fixed length, so short inputs and long inputs produce hashes of the same length. So no matter what I apply this function to, I always get the same length output from the hash function. Because of these properties, hashing is not the same as encryption. So encryption more broadly, as you'll read about in the book, means sort of coding a message, encrypting it, and then decoding it, decrypting it after. So that more broadly refers to encryption overall. A lot of people mistakenly will say things like the Bitcoin network is encrypted. That's actually not true. The Bitcoin network is essentially public. It is the opposite of encrypted. It's very easy to observe what's happening there. However, encryption plays an important role in the operation of Bitcoin. So what encryption does broadly is it hides information so it can be later revealed. Encrypt, decrypt. Hashing does not hide information. It creates a fingerprint of that information is one way to think about hashing that will be particularly useful here. So given those characteristics of hash functions, what roles do hash functions play? Data integrity. Hashes allow anyone to check whether data has changed. Because remember, if I hash some data and then it changes, even if it just changes a little bit, I'm going to get a very different hash function. So if I get that very different hash function, I'm going to know something has changed about the data. Efficiency, large objects, entire databases of data can be hashed and they will lead to one length. One letter can be hashed, same length. So we can store sort of our integrity efficiently, even for very large things, by using a hash function. So those can be all of these larger things we might want to hash can be represented by small fixed length hashes, making verification and comparison fast. So I could compare to somebody says, hey, these two massive data sheets are the same. That's going to be difficult to verify by comparing them, but if I hash both of them, if they're exactly the same, I should get exactly the same output. They are a building block for what is very important on the Bitcoin and other cryptocurrency networks and blockchains generally, is authentication and other, not just those things, but authentication could be an important in a wide variety of contexts. But one role, they are a building block for that. So we don't really do authentication alone with hashing, but they lead to what allows us to do authentication in very specific environments. Specifically, if I'm working with a stranger that I've never met, don't trust, authentication in those types of environments, which we've motivated in the past. They also allow for something extremely important in economics, which is commitment. A hash allows someone to commit to information without revealing the information. I could say, I'm going to write down a prediction on this piece of paper right next to me. Here, I actually do have a piece of paper and a pen. I could write down a prediction about what's going to happen tomorrow. But I don't want you to know that prediction because I'm going to use that prediction to make a bunch of money. And if I tell you about it, I'll make less money because you'll try to get in on that action. But I also want to brag tomorrow after my prediction comes true. So how could I prove to you that I made this prediction? Well, I could hash the prediction, show you the output of the hash, which you can't go back to the message because it's really difficult to go from the output to the input. So I could show you that now without revealing to you my prediction. And then after the prediction comes true, as of course it will, I could say, look, okay, here's my prediction. Let's hash it. Boom, we got the same hash that you got. That would be extremely difficult to do without me having that message in the first originally. So that allows for that type of commitment. A hash function can serve that sort of functionality. So in economics and game theory, commitment devices more broadly matter because they change incentives by limiting future choices in a way that others can observe and believe. A commitment works when it makes backing out costly, impossible, or easily detectable. For example, in business, a firm might commit to a low price strategy by investing heavily in large scale production capacity. So, look, I'm going to build a ton of factories. My competitors see that I'm building a ton of factories. They're thinking if Gavin actually uses all of those factories at capacity, he's going to have to charge a very low price to sell all that product. I've committed by building my factories to a low price in some sense. So that might be used as a commitment device in business. So these commitment devices show up in all sorts of places. So the fact to have a digital commitment device like a hash function could play a lot of different roles in digital sort of the digital economy as commitment devices play a huge role in the economy more generally. So hash functions provide a technological way to achieve this same commitment logic. By publishing a hash today, someone commits to specific information because that information can't be changed later, or it will lead to a different hash in a way that can be verified later. Revealing different information later would immediately be detectable. So now more specifically, hash functions in the economics of cryptocurrency, they play many roles in computing systems, but in cryptocurrencies, they are best understood as a building block because we're going to build other functionality out of hash functions. In crypto systems, hash functions are used to make records tamper evident because again, if we tamper with it, the output will change. Represent very large objects with small fixed length values. That can be very efficient if we have a lot of large things, and we'll see that plays a role on the Bitcoin network itself. These properties make verification cheap, fast, and public. Cheap, we like that in economics. Fast is kind of another way of saying cheap because time is money, right, baby? Public, we're going to get in a little more later about why that part is useful in terms of verification and in terms of the operation of a cryptocurrency network, more a little bit more later. These are all essential for systems that do not rely on centralized finance type platforms like banks. So now in the block below, we're going to go ahead and just show some of this functionality of hash functions. So let's see what we're doing. So defining a message here, the base message will be, I will bid $100. A small change message, I will bid $101. So based on what we've said above, if we apply a hash function to these two different messages, we should get very different output. So we'll see if that actually is true through example in just a second. Now, another thing is we could have a very short message and a very long message. This is 10,000 A's, and then they should lead to a fixed length output. So even though this is only 2 letters and this is 10,000 letters, we should get the same length hash output or digest output from hashing both of those different messages, even though one is very short and one is very long. So now we're going to go ahead and actually hash these things, print some stuff. I've already run it. So same message. So one thing we did is we hashed exactly the same message twice, and you can just look through this to see. So same message hashed twice is happening right here. And we can kind of verify, yep, 2C82, those are exactly the same throughout. So I put the same input in, and I did in fact get the same output. So are those equal? True. So we're testing that in the code. Sensitivity to small changes. So if our original message is, I will bid $100, this, by the way, this little b is changing that message to bytes from the computer's perspective, which is what we're going to input into the hash function itself. So I will bid 100, I will bid 101. Those are very similar, but one digit is different, right? This 0 is a 1 now. Okay, we get our original back. That's our 2C820. Look at, look at. Very different, right? These are very different outputs. That's a characteristic we like. Something that we wouldn't like at all. What if this was exactly the same as this and only the last digit was different? And then that kept, and then we did two, and then only the last digit was different again than the other two. That would be worrisome because somebody could probably design an algorithm to start going backwards from these hashes back to messages. And that would violate one of our characteristics and something that's important in terms of a verification. So tiny message, 2 letters. This is the length of the hash. 32 bytes. Here's our 10,000 A's, dot, 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 because it keeps going. That's also a 32 byte hash. So all of those characteristics we mentioned turn out to be true when we apply these hash functions to those different messages. Now, next, one thing that is built out of public and private key, or sorry, one thing that is built out of or where hash functions are used is an asymmetric cryptography, which you have already or will read about in the book this week. So that involves using public and private keys. So, and that might also be just called public key cryptography. And so instead of just having a single secret like a password, public key cryptography uses two mathematically linked keys. A private key, which is kept secret. So if I go start an account on a Bitcoin, I'm going to have a private key, and an associated public key will be created using my private key. And that creation will define the mathematical link or relation between those two things. And so two things exist. Now, what is the use of these two things that now exist, these two keys? The keys are generated together. Knowing the public key does not allow somebody to know the private key, because that would be bad. Then my private key is no longer private once I share my public key. So this one-way mathematical relationship, similar thinking about hash functions again, one way, is the foundation of public key cryptography. Public key cryptography is not mainly about hiding information, is it about proving who authorized something? So cryptography often is about hiding something. In this case, it's more about verification, authorization. So I want to just provide three concrete examples of how these will be used, and then we'll get into a little bit more about how it actually works. So let's think about authenticating a payment. So I might want to send Bitcoin to somebody, so I can use my private key to sign a transaction, proving that I authorized it. Because if I sign, I'm the only one with my private key. So something is signed with my private key, then that proves that I'm the person who did it. Now, the second step is like, well, how can we check if we signed it with the private key? Anyone on the network can use the public key that is public to verify that the transaction was authorized of the owner of the public key, which has to be the owner of the private key that's associated with the public key, through the mathematical link that was created when both of them were generated. You could also authenticate a message using very similar logic. Suppose you publish a message saying, I agree to this transaction. You sign the message with your private key. Anyone can verify using your public key that the message was created by the same party who controls the private key. So really it's the same thing, but now it's a message instead of sending Bitcoin. We could also authenticate control without revealing identity. So we could publish our public key openly, of course. Later, when we sign something with our private key, others can verify the signature using the public key without ever knowing our name, password, or real world identity. Because in the schematic and privacy in the Bitcoin paper that you looked at last week, remember, transactions themselves are public on networks like the Bitcoin network. What's where privacy really exists is breaking identities away from the accounts on the network. So we can see what the accounts are doing. What we can't see is who are the owners of the accounts. Now, given advances and changes in technology, maybe that changes over time. Maybe it has already changed a little bit. So people take additional steps to have more privacy, more separation between accounts and human beings or accounts and institutions. And other cryptocurrencies have emerged that try to sort of increase the level of anonymity and privacy on the networks. And we'll get into those later in the semester. So why do these things matter economically from an economic perspective? Well, public key cryptography changes what is possible in economic systems. It changes, remember, fundamentally, we're thinking about can we get some of the characteristics of cash in a digital money world? Now, because of these technologies like public key cryptography, the answer shifts in the direction, yes, we can get some of them back. We can maintain anonymity on a digital network without needing to use physical cash. So public key cryptography, what does it allow to happen? Transactions to be authorized without banks or platforms, without a trusted third party. Agreements to be verified without courts or identity checks. And coordination among strangers without prior trust. Cash does that. I can meet somebody in a parking lot and buy or sell them something on from Craigslist or from KSL with cash because, and I don't need trust really because they're going to hand me hard cold cash. I'm going to be holding it. If they hand me a check, if they want to use I mean, that's not exactly digital. That will enter the digital realm after the check is passed to a bank, but that requires trust. Both I need to trust the person handing me the check. I also have to start trusting some third parties at that moment. So let's go ahead and now look at some code behind these things. So in this block, we're going to generate a private and public key pair using, and these are all functionalities provided by these cryptography libraries up here. So step one, we're going to generate a private key. That's the first step in the process because the public key comes from the private key. This is a large random number generated using a specific mathematical structure, and there's different structures we could use for public-private key cryptography. There's not only one. Elliptic curve cryptography is the name of what's being applied in this function, elliptic curve right here. Generate private key so this is a variable we're naming. We're calling our private key private key. This is functionality provided by the library that generates a private key for us using this mathematical specification, basically. So in reality, I would not be doing this on a video on YouTube because I would definitely want to keep this private key, which I haven't showed yet, absolutely secret. Because the second the private key isn't secret anymore, then we actually lose all of the characteristics that we just covered in the last block. So step two in this process would be then deriving the public key from the private key, making the mathematical link that was mentioned above. Here we go, public key, private key dot public key, because we need to reference this private key we've already created in the creation of our public key. This is a function. This is our variable, the private key we just created. That needs to be there to create the correct mathematical link when we apply the public key functionality to create our variable public key right here. So step three, serialize the private key to bytes so we can display it, because this private key is something that would not be easy to look at otherwise. So in real systems, private keys should never be printed or shared, as I mentioned above. So just in case you happen to forget that, hopefully that should be obvious by the name. And then step four, we're going to serialize the public key in the same way. This is just so we can kind of display them right here. And then here is what those guys look like in bytes. So this is just kind of a way that we can look at these things in bytes. And now we can, so now in the next step, this is just the creation of a public-private key pair. That's all that happened in this code. Now in this code, we want to go ahead and sign and verify a message and see how that actually works. So step one, we'll define a message. So message, here again, we're just changing the message to bytes. I authorize this transaction. That'll be our message. So now we're going to apply a hash to that because we're going to hash the message, and that is actually what we will end up signing later is the hash of the message. So this is just a function to use to actually hash something. And now we have the message hash in the hasher digest right here. So now step three, sign the hash using the private key. This is the act of authorization. So this is the digital signature that's referenced in your book. So in order to sign something and to verify it, I need to use my private key. So the signature, we're going to take that private key. Again, this is a variable we created above, right? We're going to use our private key to do this function, which is signing. And we're going to sign the message hash, which we created above. And then this is just the particular hash algorithm that's being used. And so this is the actual digital signature occurring right here. This is the step that we've said, good, we've signed the message. Later, this message could be verified. So now let's go ahead and look. Oh, and then there is a verification step too. So we're going to try, because this could fail. That's why we have this code here. Try this. If this works, then we're going to print, sweet, we have a valid signature. If this fails, we're going to have an exception, and it's going to say, no, that did not work, so it was invalid. So public key, remember, this is a variable we created above using our private key. So there's a link between this public key that I have highlighted and the private key that we started with above. That link was created upon the generation of this public key. Now we're going to use some more functionality provided, verify the public key. And so what do we need? We're going to look at the signature. We're going to look at the message hash, and then either it will be verified, yep, it's valid, or it won't be verified and it'll be invalid. So let's go take a look. I authorize this transaction. Here is the hash from that. Notice it is the same length of all of the other hashes that we did above. This is what the digital signature looks like. And then the verification step worked. It was valid. So let's see what happens if we use the wrong public key. So first of all, we have to get a wrong public key. To get a public key, we need a private key. So to get the wrong public key, we need the wrong private key. So let's create a wrong private key. From that, we create a wrong public key. And then we go ahead and we try to verify the signature above with the wrong public key. Let's see what happens. Verification route, invalid signature. That one didn't work because we got here. So this failed. And that's why we ended up with the invalid one. So if somebody tried to verify, so if somebody tried to basically say, hey, I signed that message over there. And then here's my public key, check. And you did this. No, you didn't sign it because this was signed somebody with a private key that is not associated with your public key. So verification will also change if the message changes. Maybe I send out my message, somebody changes it. I authorize both transactions because remember the original message is I authorize this one transaction. Somebody might say, hey, I'm going to add a transaction to Gavin's whole doohickey here, and I'm going to get some money out of this. And I'll just change the message to I authorize both transactions. So let's go and make a tampered with message. I authorize both transactions. We have to get the hash of our tampered one. Let's try to verify that with our correct public key now. We're back to our correct public key because here we're just trying to say what happens if the message was tampered with. We have invalid signature, message was changed, basically. So now let's just step back. I know that's going to be something that you'll want to think through each of those things. Don't focus on the code, focus on the logic that's occurring through. Think about, okay, this mathematical link exists. It exists between these two. It doesn't exist between these two. Why is the tampered message causing problems? Think at the logical level, not the coding one. If you are working on the assignment and run into trouble with the code, please reach out to me. I'm happy to help with those things. So what did we just verify? In the previous blocks, we saw that a private key can be used to sign a message and will be used to sign digital signatures. A public key can be used to verify by anyone to verify whether a message or a signature is valid, basically. Verification will fail if the wrong public key is used or if the message is tampered with or changed in any way. This means that digital signature proves three things at once. Authorization, the owner of the private key approved this exact message, exactly those words. Even if we change it a tiny bit, it will fail. So it's exactly what was approved. Integrity, the message has not been altered since it was signed. And in non-repudiation, the signer cannot later deny having authorized the message. Maybe tomorrow after my prediction, I say, oh yeah, this is exactly what I predicted. We hash that and get a different hash. So that would be a clear way of saying, no, this is not what you predicted because it's not verified, basically. That could be something that could be done with, and that is, we could just use with hashing, as I explained above, but digital signatures could be used there as well. So let's think about connecting this to week three a little bit. In week three, banks and payments, we had banks in these payment networks. What did they do? They verified who was allowed to spend money, checked that transactions were valid, and enforced authorization through institutional rules. Here, those same rules are performed by cryptographic verification instead of intermediaries. No bank was needed to check an identity, but identity was verified through the mathematical relationship between the private key and the public key. Identity in the sense of, is the person who owns this account or owns this message actually the one affiliated with this message? We can verify, so check the identity linked to the messages in the private key, but not necessarily who the person or firm or institutional or agent who's affiliated with that private key. So that is an important distinction. We can approve the transaction, and so and the no bank, so no bank was needed to approve the transaction above. Those like transaction meaning sending a message or saying I approve this transaction or enforced the authorization at all. We have a digital or a cryptographic way to authorize things. All of those were essentially replaced by mathematical rules implemented through computer systems, but with major economic implications, especially in the realm of finance. So the big picture, digital signatures replace institutional authorization with public verification. That's kind of, we still aren't going all the way there yet, but that's what Bitcoin is going to get at. It's going to say, okay, normally we go to a single bank and they say, yep, this is an authorized transaction because Gavin logged into his bank account, so forth, and he verified this, and he's the one who sent this money. In this case, we're putting everything out in the public and saying, this digital signature is tied to moving these Bitcoin from an account A to account B. Anybody can go ahead and use the public key that's available to them to then verify that transaction. What we're going to think about next is, well, why would anybody do that? If people are interested in using the Bitcoin network, they want to trust it. So they might say, okay, I'm going to check. Is this real? Is this actually a verified transaction? Oh, yeah. So this digital signature is associated with this public key, which is the public key associated with those Bitcoin. So that's a verified transaction. We're kind of putting it on a poster board for anybody at any time to check. Now, if somebody checks that and it isn't verified, that will lead individuals to say, hey, this system, something is wrong with this system. This is not a valid transaction. And later, as we get into blockchains where the Bitcoin network lives, we'll have what's essentially an invalid block of transactions if that is found to be true. So the shift is central. This shift is central to how cryptocurrencies work and explains why Bitcoin transactions are publicly visible. So anybody could try to verify a transaction. Irreversible, because you can't go backwards on this stuff, as we've seen above, and not dependent on banks or payment processors. Those are replaced by essentially an open system where everybody can see and try if they want to verify transactions. Um, and this is, I decided to be not do more after that block. So please don't hesitate to reach out if you have any questions about this stuff. This one's probably the hardest lesson so far, but a very important building block. We're going to come back to these issues a lot when we talk about the characteristics of blockchains, particularly the Bitcoin blockchain. So it will be important to get a pretty good grasp on these. However, they're complicated and it does take some thinking and time to truly embrace them. So please just reach out if you have any questions or confusions about those issues. Okay? And I will see you guys next time.